Everyone. As we continue with our marathon, our next topic is on obtaining the Unobtainium with high entropy alloys with Youping Gao, founder and president of Castheon, and Sunil Badwe, chief metallurgist of 6K. Dr. Gao founded Castheon Incorporated to advance the state-of-the-art in additive manufacturing and industrialization. He is the fellow of the Laser Institute of America and Additive Manufacturing Consultant to LLNL. In his previous position for over 21 years, he worked diligently on building Rocketdyne's advanced manufacturing capabilities from large complex structure brazing, hip brazing, joining, thermal processing, advanced laser material processing, powder metallurgy to additive manufacturing. As fellow and manufacturing discipline chief, he led the AM development and maturation effort and became the first in the nation achieving NASA certification for production of additive manufacturing of mission-critical components for manned spaceflight. Dr. Badwe is a metallurgist with diverse experience in various materials and processes, including additive manufacturing. His experience includes metal casting, powder metallurgy processing, and alloy development for additive manufacturing. He holds a patent for new alloy development, duplex stainless steel powder for sintering applications. Sunil has a BS and MS in metallurgy from University of Pune, India, and a PhD in material sciences and metallurgy from the University of Nevada in Reno. Welcome.
Thank you, Roxanne.
And thank you.
So we'll be presenting manufacturing of high entropy alloy spherical powder with a new technique that 6K has developed. So I will be presenting along with Dr. Gao from Castheon. So we are technically in different dates. I'm presenting from Pennsylvania while Dr. Gao is presenting from California. So this is just outline of what we will be presenting. We'll be presenting a little bit about 6K, who we are. Then we'll be presenting about what our system is, what our unit is, and then what is high entropy alloy and why it's important. And then we'll go to the journey of high entropy alloys, the 6K journey of high entropy alloys for producing spherical powders. And then Dr. Gao will present a little bit about Castheon, and then he will present his experience with printing high entropy alloy produced by 6K. So 6K is a company that was founded in 2007 based on microwave-based plasma technology. In Boston, there is a headquarters and there is an innovation team. The innovation team works with the plasma technology in two different categories. One is for additive materials, and the other one is for battery materials. We also have acquired a company in Pittsburgh last year. I will talk about that company a little bit later. Let's see what is Unimal and how it works. So 6K Unimal technology is based on microwave coupled plasma. So basic difference between microwave plasma and other existing plasma technologies is the plasma cross-section of plasma. In the microwave coupled plasma, we have almost uniform plasma in cross-section from center to end. So it is uniform temperature, and there is basically then there's a maximum working area there. So what happens there, that we can pass one time the material through plasma, and then it is processed. And as against other plasma systems, they have discontinuous plasma. There is a cold spot inside in the center of plasma, and that means that the material, not all the material experiences the same heat history. So our plasma can use different types of environments, different types of atmospheres, like reducing atmosphere, oxidizing atmosphere, or neutral atmosphere. And with the help of that, we have ability to spheroidize powders, and also we have ability to synthesize different materials or different composite powders with our plasma system. So this is the little bit about the company that we acquired in Pittsburgh. The company is complementary to our technology. This company produces. This company actually recycles machine waste from various subtractive manufacturing techniques and turns into an highly engineered compacts. And basically, this company works with titanium, and it produces the highly engineered titanium compacts for use in aluminum smelting industry for titanium alloy additions. And this aluminum alloys, they are used in various sectors like automotive sector. So if you have like a Ford F-150, then you have rolled aluminum sheets in there. Then it is used in defense and aerospace applications, and also it is used in medical applications such as ventilators. So what we have done, we have developed our powder processing or powder manufacturing technology by combining this expertise in this company to process the scrap with specialized milling techniques to desired PSD. And then we use that as a feedstock for our UNMS spheroidizing system, where we can spheroidize those powders. When in this example, it is shown that it is 718 powder right from scrap to final finished powder. We can produce highly spherical powder without any satellites, and with a high powder physical properties. And this is showing the capability of Uniman handling different types of feedstocks, right from certified castings to regular powder, even the used powders and the spongy powders. We can use different types of feedstock, and then we can produce different highly spherical powders. These are examples here that we have produced from different types of feedstock, like titanium 64, inconel 718. And at the same time, we can use mechanically alloy powders as a feedstock and produce high entropy alloys. So high entropy alloys are different types of different family of alloy, which are basically, it is termed that high entropy alloy. If you can see this little graph there, a little plot there, high entropy alloys are generally which have entropy of mixing more than 1.6 R. And that corresponds to minimum 5 elements. On x-axis, you can see number of elements in equiatomic compositions in the alloy, and on y-axis there is this entropy of mixing. So where there is an onset of linear portion of that plot, that's termed as high entropy alloys. So high entropy alloys basically it gives us very large design space. If you see this ternary phase diagram, the conventional alloys are concentrated at the apexes of this ternary diagram. So if you see this yellow section in this figure is that where the conventional alloys are. The green portion is non-equiatomic high entropy alloy, and the red dot in the center where it is equiatomic high entropy alloys. So basically, high entropy alloys have very, very high design space, which is not utilized today, and that we can utilize for different types of alloys, which can give you various combination of properties. So basically, the high interest in high entropy alloys is because of it on lab testing or lab research. It has shown that it can produce different types of properties which are not achievable in conventional alloys, and basically the combination of properties which is not available in conventional alloys, such as. So this slide shows what kind of properties high entropy alloys can produce. So this is a very congested slide, but what we are trying to show here is why or what's the importance of high entropy alloys. So if you see the first top left figure, where it is showing that the relationship between it is a plot of yield strength and density. And there you can see that high entropy alloys is at the top right corner. So that means that it is showing that it is outperforming titanium alloys, or even it is close to the bulk metallic glasses. So similarly, the lower left figure it is showing the relationship between tensile strength and pitting potential. So where it is showing that high entropy alloys have high pitting potential and high strength, high tensile strength than nickel-based alloys, nickel-based superalloys. This is particularly applies to oil and gas industry or undersea applications. And similarly, the other plots, they are showing a relationship between specific strength and Young modulus. And on the right side, right two figures are showing the relationship between fracture toughness and strength of entropy alloys, high entropy alloys. So even if these high entropy alloys have high properties or interesting properties, why is it not in the mainstream production or application? So one of the things is basically all alloys or conventional alloys are manufactured using melt-based technologies, either by induction melting or arc melt. So what happens in high entropy alloys, since the elements are equiatomic concentrations, sometimes they exceed the solubility limits of each other, and that becomes difficult to produce by melt-based technologies. Sometimes the high entropy alloys have elements that have different or drastic temperature difference or melting temperature difference. Like in our example, it's chromium and copper. They have very drastic temperature melting temperature difference, but then they are present in equal amounts. So such alloys, they are either difficult or impossible or expensive to make with melt-based technologies. And basically for powder production, especially, currently powders are produced by either gas atomizing or plasma atomizing. Both are melt-based technologies. The input for gas atomizing is ingot, which is produced by melting, and input for plasma atomizing is wire, which is also made by melting. So the alloys which cannot be are difficult or expensive to manufacture by melting, we cannot use gas atomizing or plasma atomizing. Otherwise, it will be more expensive. The other limitation of gas atomizing or plasma atomizing is the yield. So especially for additive manufacturing, very popular particle size distribution is 15 to 45 microns. And that's in either gas atomizing or plasma atomizing, the yield is maximum 30%. So 60% is oversized or waste. It is recycled. And that makes these processes expensive. So for HES, which are in development stage, or even for existing alloys which people want to modify for printability, the atomizing is most expensive method for them for trials. So what we are bringing into picture is the mechanical alloying. So mechanical alloying is a process that was initially developed for oxide dispersion strengthened alloys, ODS alloys, where the alloys are mixed with very fine or nano-size oxides, and then they are producing like a composite ODS alloys. So this is basically a solid-state alloy, which means that there is like endless compositions that we can manufacture by mechanical alloying. So it depends on the mechanical or kinetic energy of particles they are bombarding in each other, or they're forced or mechanically forced to form the alloys. But the main drawback of this process is the powder produced from this process is very, very flaky and highly irregular. ultimately it has very low density, and which is not usable for additive manufacturing or hot isostatic placing. That's the industrial processes for powders. So basically what happens here is when you produce mechanically alloyed powder, it can be used in spark plasma sintering, and that's what people are using for research. And this process, spark plasma sintering, is not industrial process. And then this powder cannot be used for other industrial processes like MIM, tape, or additive manufacturing. But as soon as you have this powder in spherical form, it can be used for different industrial processes or commercialized processes that we know of today. And that's what we can, that's what the 6K brings this value to have these kinds of alloys in mainstream application at scale. So what we are doing for this is our new way of developing new alloys. It's combining mechanical alloying with unimelt plasma spheroidizing, where we can mechanically alloy different elements to form an alloy, and then we can spheroidize that alloy to form a spherical powder, which ultimately can be used in different types of manufacturing processes that we know of today. So here for demonstration, we have taken a alloy which has the components that has different drastic melting point differences like chromium and copper. So in this case study, what we have demonstrated, we can make this alloy. We can manufacture this targeted alloy that's 25% iron, 17% chromium, 17% cobalt, 17% nickel, and 16% copper. So this is near equiatomic composition. We have successfully manufactured by mechanical alloying, and then we have successfully spheroidized. And after spheroidizing, we have also printed it with the help of Castheon. Castheon actually designed and printed this tube that shows 6K and 5 elements on other 5 sides. So these are the results, or analytical results for the HA powders or spherical powders that were produced for demonstration. And as you can see, the powder chemistry almost matches the targeted chemistry. And powder physical properties like flow, AD, and 3D, they are also in line with the requirements of additive manufacturing. One of the important things that we have noticed that by spheroidizing, we can actually homogenize the alloy more. So this is shown by this XRA plot. In this XRA plot, the blue line is a mechanically alloyed powder that's used as a feedstock for Unimelt for spheroidizing, and the red plot is for spherical powder, or spheroidized powder. So you can see in this marking, there are 2 markings in this marking, that on the blue line there are very, very weak peaks that are very prominent after spheroidizing. So that actually shows that there are different phases forming by reducing the element. So reducing the elemental peaks, you are forming an alloy, and these peaks are representative of that alloy. So we are still investigating this with further techniques like TEM and SEM, but based on XRD, we can say that we can actually homogenize this alloy during spheroidization, and that means we can actually reduce the milling time. So with this, I'll hand it over to Dr. Gao for his experience with printing this powder.
All right, Sunil, thank you so much, and good job. I got 2 minutes to go over charts and show Castheon. Castheon is funded by the sole purpose of advanced additive manufacturing and to do the in-depth additive manufacturing study from the grain morphology control to the process robustness for the defects and defects eliminations. And so we do a lot of high temperature material. My background is in rocketry industry, so we do a lot of high temperature material, refractories, nickel, cobalt, iron-based super alloys. We also do the 7 series aluminum and coppers as well, GR copper for the rocketry combustions. Let me see, next chart. All right, next one. So we really focusing on how to optimize the green structures of the additive manufacturing. So on the chart, what you can see is on the left is the additively made material, on the right is a forged material. And what you can see is, you know, the additive looks awful, and there looks just, this is as welded microstructure, and depending on how you etch them, and you're going to see a different grain size. And so the grain size is typically pretty large, about ASTM grain size of 4 or 5. And but if you heat treat them, what you can see is this is after heat treat, we were able to convert this 100%. And it's not all the additive alloy can be converted 100%. There's a certain copper alloys never converts. There's a certain aluminum alloy never converts, and there's a certain solid solution strength materials very difficult to convert. And so what we're focusing on is for most of the applications, we're converting them to have the isotropic material properties. And so in the additive side, what you can see is it's actually more homogenized than the raw material. And the other things we explore is to find the strengthening mechanism of this. And so this is the Hinge Alloy, Hinge 230. On the left is additively made. And so what happened is the Hinge alloy has 14% tungstens and high carbons. And so what happened is this material is strengthening in addition to solid solution strength. It's solutioned by the stable carbides. And in the raw form, the carbide already formed. In the additive form, carbides and the tungstens are truly stay in the solid solution. So next things you do is if you heat treat them, and you can see uniformly precipitation of the carbide. On the other hand, what you have is you have this large carbide already formed during the traditional mill process, the casting process. So you have to do an extensive thermomechanical reduction to get rid of those, and because this caused the grain boundaries laced up with this and cause the sensitization of the material. So you basically lose the high temperature strength and you lose corrosion resistance. And so the other things we emphasize on is we are a machine agnostic developer. So everything we developed, we're able to transfer over to different machines. And most time we obtain the in-family material properties. And so we developed on our concept laser machines or on the Renischel machines, we transfer over to the EOS machines and the metal fab machines and the SM Solutions machines. There was no problem. We retain that material property. So we're developing process is a machine agnostic, whether it's a 2D optics or 3D optics, we take care of that all. And so we have this development protocol. It's based on a physical metallurgical process. We developed this, and so it's called a gallblock, and we have the model. The model has been shared through the NASA system, through the universities, and a lot of people using them. Initially, it was for quick parameter development, and then later on to become a process monitoring hardware. So you can easily analyze this piece and this give you a sign, give you a trace of how this material behave. And so we print a lot of the different things and of this. And now going back to the high temperature applications, right? So previously I mentioned on the Hinge 230, we were able to get a far stronger Hinge 230 and a far higher temperature capable Hinge 230, just because we control the carbon and the tungstens and retain them in a solid solution. So in the material world, in the metal world, it's all how you play with the solid solution. And once you can make solid solution in the net shape, you're the king. And so this is another example, and this is the niobium C103. So a couple of years ago, we developed this niobium C103, which is a refractory material. And what we found was, this is the two pictures above on the metallography is the green structures of the printed, 3D printed. So the difference is in the middle is the as printed microstructure. And on the right, this material has been exposed to 2,900 degrees Fahrenheit for 2 hours. So what we're seeing is this is an extremely stable material. So if you look at the background, the raw material, the microstructure, I don't know if you can see my mouse moving, and maybe I can click it here. Yeah, I can click here. Use the laser pointer. So you can see the raw material grain sizes are finer, but the thing is at 2,900 degrees, grain start to expand. So explosive grain growth and grain boundary sliding, you lost the creep resistance. So now you compare to the raw material and additively made material, and in each category, in each temperature testings, this additive made material are far stronger than the raw material. So that gave us a chance to create a new type of higher class applications. So we're trying to apply this to the high entropy material. And so you can say we not only develop the material itself, we develop process and assess the printabilities. We're also bring the material to the final testings. So we give the complete development of this. So now going back to the high entropy alloy. I can get rid of the laser mode so I can, okay. And so this is the second generation high entropy alloy 6K, and Sunil has been working on, and so it's quite interesting. The first time we can make this, but it's not always really dense. And the second generation is what you can see is we can make this overall more than 99.75% dense, and the as printed microstructures shows the properties. It's not bad, and so those are the things what we have tried to explore to use this process. And I think the great things about the 6K process is, so typically if you're researchers and you can buy all the elemental forms in the form of powder. So the high entropy alloy gave you a great chance of mixing all different powders together, and using 6K's process, you can create a desirable chemistries, and you can quickly testing them using additive. In the other process, I mean, if you have to casting them, you have to make all the adjustment, it's going to be a headache, but this one is far efficient to explore the material, especially in the multi-component high entropy alloy arena. So next is, let's see, let me see, how do I go to next one? Some reference, we appreciate everybody working on this, and we'll leave some time for the questions, Q&As.
Thanks, Sunil. Thanks, Youping. I'm not real sure. I thought I saw a question actually come up in the chat. Avi Cohen had posted in the chat an interesting view and details of metal materials in AM. I'm not real sure if he had a specific question on that, but if I pop back over to the Q&A, one of the questions we've got is, can HEAs hold the equiatomic structure during the powder bed fusion process?
I think the answer is yes. What we found was that there's no skewed alloying vector factors for this, and it applies particularly to this alloy. And so this alloy doesn't have the really weird low vapor pressure component in there. So this is not bad. And even with the other material, like we do on the refractory material, the titanium retains 100%. Where you go into the EB process, titanium pretty much is gone. So in this case, we can retain the original chemistry.
Okay, great. Simon had asked, mechanical alloying can assist super solid solution, but once the alloy melts via laser melting, how do you overcome intermetallics formation?
That's so depends on the alloy chemistries, and sometimes you can control, and sometimes you can't control. In this case, there's there's no preference only because they're mixing pretty good. So we do see some segregations, but they're still in the alloying form. So we haven't seen this strong formation of the intermetallic yet, but I'm sure once you start to play the chemistries and you're able to scale to one of the directions, you're gonna hit some intermetallics forming.
Okay, great. We've got a couple more questions, but we'll forward those to you both. We're out of time for this session, and we've got a lot of people desperately waiting to chat with you guys and others in our networking session. So appreciate everything, and we'll get these questions to you. Thanks to you both.
Thank you.
Roseanne, thank you.
All right.
All right, you must be tired.
Yeah, just a little bit. That's okay. This is fun.
Okay.